Okay, so now on to chapter 14, problem set with acids and bases. So here we go, identifying Bronsted-Lowry acids and their bases. So the idea of Bronsted-Lowry acids is it's a proton donor. Acids are proton donors, and bases are proton acceptors. So the species that loses a hydrogen, in this case it's the sulfuric acid, the H2SO4, it goes from H2 to H1. So it's losing a hydrogen, and water is going from H2O to H3O, so it's gaining a hydrogen. So that's making it a base. And then the conjugates are just in the opposite direction. Although sulfuric acid, the first proton, the first hydrogen, is a strong acid, it's not reversible. It's not a reversible reaction. But the conjugate base would still be, although in practice it would be impossible because it's a one-way reaction. But the conjugate base in the reverse direction would be the bisulfite ion, as shown there. Um, I'm sorry, bisulfate ion there. And then the hydronium ion would be the conjugate acid going the back way. Now going back to the next step, the bicarbonate, well, this is our, oh wait, so it has it as a bicarbonate, should be a bisulfates. Oh no, oh it has it as, oh the second one, I see. So I thought it was doing the two steps. The bicarbonate anion, it's in this chemical reaction forming carbonic acid. The bicarbonate anion is the base. It's the proton acceptor, and water here is the proton donor, makes it the acid. So in this one here, where the hydrogen, the bicarbonate HCO3 goes from H1 to H2, so it's accepting a proton, accepting a hydrogen, so it's a base. Water here, H2O goes to, well, I mean, it's OH minus, but it's lost a proton, lost a hydrogen, that's the acid. And then in the reverse direction, the carbonic acid H2CO3 in the other direction is acting as an acid. Same thing with the hydroxide. Hydroxide is absorbing a hydrogen, so it's a base going in the opposite direction. So what's the molecular equation for overall reaction between hydrochloric acid and aqueous calcium hydroxide? So looking at this, and right away when you write it down, you can see that there's two hydroxides in calcium. Remember, calcium is an alkaline earth, and hydroxide is a -1 polyatomic ion, so you need two hydroxides there in the calcium. And then to form waters there, you're going to need 2 parts of acid. So when you balance this, and I could just kind of balance it using the units, you're going to need 2 units of acid to neutralize each part of calcium hydroxide, because there's 2 OH minuses in the calcium. So you have a 2 there, and then it forms 2 waters, and then the calcium chloride salt. So let's do another one for hydrochloric acid with potassium metal and hydrobromic acid with sodium oxide. So start with potassium metal. So acids with, hydroiodic, sorry, did I say hydrochloric? Hydroiodic. So reactions with acid with metal form hydrogen, assuming the metal is more active than hydrogen. If you remember the activity series, well, we haven't gotten there yet, I guess. The activity series when we talk about oxidation, the noble metals, things like gold, they don't react with acid, but most metals do react with acid to form hydrogen. So start with this one. So hydriodic acid, or HI aqueous plus potassium K metal makes hydrogen gas, and then the potassium iodide salt. So we balance it. You have balance the hydrogens. You need to have 2 hydrogen iodides and then 2 potassium to form 1 unit of H2 gas, and then 2 potassium iodide solution. So looking at that, and the kicker there is the hydrogen then is what pushes it over to the have the full units. So I'm balancing it. So now with the sodium oxide, so hydrobromic acid and sodium oxide. So oxygen tends to be -2 and sodium tends to be +1. So you need to have 2 sodiums to counteract that -2. And then this is the reaction here. So you have an acid base, you form water and a salt. So, and the sodium bromide is balanced properly there for the ion charge. Sodium's +1, bromine's -1. So now, looking at this, you're going to need, so because you have the two sodiums there, you're going to have to have the two sodium hydrobromic acids to react with the two sodiums. And then if you see all balances, it's because you have the two hydrogens then to make one H2O and the one oxygen to make one H2O. And then with the two bromines and the two sodiums to make two sodium bromides. So looking at that and balancing it that way. So now we're going to do titration. And with titration, it's a way of figuring out how much of a certain kind of stuff is in something else. And if we understand how, like, the concentration of one of the things we're looking at, and then from the amount, we can figure out from the amount of the stuff that we know, and if we know the identity of it to what the stoichiometric ratios are, we can figure out how much of the other stuff is in there. So if we have 10 milliliters of an unknown concentration of hydrochloric acid solution, but we take 12.54 milliliters of a 0.1 molar sodium hydroxide solution, what is the concentration of this unknown solution? So we know the amount, the volume and concentration of the sodium hydroxide, and we know the volume of the hydrochloric acid. And from this, we know then that we can figure out from this is what the unknown concentration of the solution is. So let's do the math. I've been always doing the math at the end. What should we suggest? What this is. So if we have 10 milliliters and we're taking 12.54, so we know the concentration of solution is going to be around 0.1. And we need a little bit more of the 0.1 solution, so it's going to be a little bit higher. So we should expect something around 0.1 molar, but we expect it to be higher than 0.1 molar. So going forward. So and there's also a 1-to-1 concentration between, or 1-to-1 molar conversion between hydrochloric acid and sodium hydroxide. So also think in terms of moles. So moles equals moles. Moles acid equals moles base, and these are all monoprotic and monohydroxide as far as acids and bases. So we would get the moles of sodium hydroxide, convert to the moles of hydrochloric acid, and think the moles of hydrochloric acid divided by the volume of solution to get the concentration. So doing that, and let's do the dimensional analysis. And starting off with the volume of sodium hydroxide, multiply the concentration. Now we have the moles of sodium hydroxide, and now we have a 1-to-1 molar conversion between hydrochloric acid and then we have the number of moles of hydrochloric acid divided by the volume of the solution, and we get 0.125 molar. And this makes sense, and I did the analysis before this time. I know I let it do it at times I do it in the aftermath, but if you see how my brain is kind of thinking that, does this make sense? And it makes sense that we expect it to be about 0.1, but a little higher because we need a little bit more sodium hydroxide. That's the kind of analysis you can do and make sure that it's done correctly. So that's how you can kind of check your answers. You don't have to check your answers this way, but I mean it helps. So it also lets you know if you've kind of done it correctly. And if you have a test and you're going through it, and if you have time to go over your answers and kind of make does this make sense? And if it doesn't make sense, I probably did a calculation misstep somewhere. So let's determine the amount of hydronium ion in acid solutions. So what is the hydronium ion concentration of each of these? We have 1.5 molar hydrochloric acid, 3 molar acetic acid, and 2.5 molar nitric acid. So first one, so it's strong acid. What are the strong acids? HCl, HBr, HI, not HF. HF is a weak acid, believe it or not, but not hydrofluoric, but the alkali acids, the halogen acids with the exception of fluorine. So hydrochloric, hydrobromic, hydrotic. Perchloric, HClO4, H2SO4 sulfuric, and HNO3 nitric. So those are the strong acids. Just memorize those, and everything else is a weak acid. So that means acetic acid is not one of those. It's a weak acid. So it's a weak acid. So we know that the pH of the hydrogen ion concentration of 3 molar acetic acid is going to be significantly less than that. And in future classes, we can show you how to do that calculation. But for this class, just realize that it's going to be less than 3 molar. And 2.5 molar nitric. Nitric's a strong acid, so which means it completely ionizes. Therefore, the 2.5 molar nitric is, in fact, 2.5 molar in the hydronium ion. So same thing with the base. So we have 2.25 molar potassium hydroxide. We have 0.35 molar methylamine. And we have 0.025 molar strontium hydroxide. So the strong bases are a little easier. It's just the alkalis and alkaline earth hydroxides. Everything else is a weak base. So for potassium hydroxide, it's an alkali, so it's a strong base. So the 2.25 molar potassium hydroxide is in fact 2.25 molar in hydroxide. So now the 0.35 methylamine, it's not a strong base, therefore it's a weak base, which means the solution is going to have a lower than 0.35 molar. That 3.5 molar. Sorry, it'll be less than the 0.35 molar hydroxide ion. In future classes, you can learn how to do this. You have to use an equilibrium constant and then calculate out that way. We won't teach that in this class. So now on to strontium hydroxide, 0.025 molar strontium hydroxide. This is a strong base, but also note that there's 2 hydroxides. So it's a strong base, so there's 2 hydroxides, so we have to double the concentration of the strontium hydroxide to have the concentration of the hydroxide, and then it's going to be 0.05 molar. So keep that in mind when you're doing that, and with the alkaline earths, there's going to be twice as much hydroxide for the alkaline earths than the alkali metals. So let's use the kW for water in the calculations. Find the hydroxide ion on each of these, determine if the solution is acidic, basic, or neutral. So generally speaking, just looking at this, I can already tell C is neutral because, and assuming it's at 25 degrees Celsius, so probably implied by that, but kW is 10 to the minus 14 at 25 degrees Celsius. If you change the temperature, you change kW, but assuming it's at 25 degrees Celsius, C is neutral, and I'll show you the math in a second. C is neutral, and remember the negatives, so actually the -5, that's more concentrated than -7 because of the negative exponents. So A is acidic, and B is lower concentration than neutral, than 10 minus 7. B is alkaline or basic. So just looking at this, but we have to go and do the calculations real fast. So A, you basically take kW divided by the concentration of the acid, and we get 1.3 times 10 times 10 molar, and that's the hydroxide ion solution. So the hydroxide ion concentration in solution. So and because of the size of that, this is acidic. So because the hydronium ion is greater than 10 to the minus 7. So remember the negative exponent. So the higher the negative exponent actually means it's lower the value. So B is the other way. Well, it's the same thing. Solve for hydroxide, kW divided by the hydronium ion concentration, and we get 6.7 times 10 to the minus 6 molar, which means there's more hydroxide than there are hydronium, which means this is a base. This is alkaline. And then 10 to the minus 7 molar, it's neutral. So that's a C, it's neutral. That's the definition there. Also, we'll talk about pHs in a little bit, but pH is 7. So C is neutral. So let's do the pH of these. If it's acidic or basic, so A being 1.8 times 10 to the minus 4 molar, and B, acid concentration, I mean the hydronium ion concentration, 7.2 times 10 to the minus 9 molar. Now we do the pH. The pH is minus log of the hydronium ion concentration. So in your calculator, type in negative sign log of then that value in parentheses, and you get 3.74. Now note something, 3.74 has 2 sig figs, so the numbers to the left of the decimal point for pH and POH do not have values. That is just the exponent. So only the numbers to the right of the decimal point in pHs and POHs carry sig figs. So 3.74 pH actually has 2 sig figs. So please keep that in mind. And same thing, that's A is an acid. So B, same thing, minus log that, and you get 8.14 for 2 sig figs. And this is greater than 7, therefore it's a basic or alkaline solution. So let's go backwards to get hydronium ion concentration from pH. Depends on your calculator. You can do inverse log. I usually just use 10 to the blank. So you can just do 10 and then the caret thing for the 10 to whatever value, and then you have to put the minus. You have to put in 10 to the minus 4.8 and then hit enter, and then you get 1.6 times 10 to the minus 5 molar. So however, I do method 2. I do method 2, I guess, as I should say, whenever I do these. But you can use the inverse log too. That's fine too. That's equally as valid. So let's do the same thing with hydroxide ion concentration. What's the hydroxide ion concentration with solution that has a pOH of 8.55? And then same one, either inverse log or 10 to the whatever, and then you get the same answer at 2.8 times 10 to the minus 9. And notice something, that the 8.55 pOH, that has 2 sig figs. So the number to the left of the decimal point does not carry any sig figs. That's just the exponent. So if you have a pOH of 12.55, that is in fact still 2 sig figs. So even if the number to the left of the decimal point goes over 9 to 10, 11, 12, then that's still, those numbers still don't count for sig figs. It's only to the right of the decimal point. Please keep that in mind. And with that, we are at the end of this chapter. Thank you for listening.